So yesterday we talked about sequences, right? So roughly speaking, what's a sequence?
A series of numbers.
A list of numbers. Okay, don't use the word series because series means something different, okay? So a sequence, roughly speaking, is a list of numbers. And that sequence converges if as n goes to infinity, your list of numbers goes to a specific place, right? Does that idea make sense? Okay, what we're going to do today is we're going to talk about something called series. And when you find it, a series is an infinite sum of numbers. So first of all, one question might be like, how the heck do you add an infinite number of things? Like, does that even make sense? One at a time, but you can't actually add one at a time, right? So the question, what would it mean for an infinite number of things to sum up to a number? So there's something called Zeno's paradox. I think it's a pretty good introduction. Have you guys heard of this?
No.
Okay. So maybe it's like the hotel, but I like to think about this is us. We're over here working on our math class, and over here, I made these notes for spring break, but it also applies to winter break. So we'll call it spring break. Make a flower. So you get to spring break this way. You go halfway to spring break. That's a distance of 1/2 unit of something, right? And then you go half of the remaining half, which is a quarter, right? And then you go half of the remaining quarter, which is an eighth. And then a 16th, and then a 32nd. You always got like a little bit to go, right? But what would this 1/2 plus 1/4 plus 1/8 plus 1/16, if I was able to add up that infinite number of things, what does it have to add up to? One.
One distance between us and spring break.
One unit of measure between you and spring break. Does that idea make sense?
But you never actually achieve spring break.
But you never actually achieve spring break. You're always just a little bit shy. Isn't that depressing?
No,
Yes.
that wouldn't really work because once
Of course not. In practicality, no. But does the idea of that you're adding an infinite number of things kind of make sense?
Yeah.
Okay. So, all right. So here is the notation. So this big old sigma sign you guys have seen before, right? This number tells you what to start with. Some of our sums might begin at 0. So you might actually plug 0 into a function. So it just happens. Now, the way we define that a series converges is we take this series and make it into a sequence. And this makes sense if you just think about, if I was given an infinite sum, how would I estimate it? Well, I'd add like the first thing, and then I'd add the first 2 things, and you add the first, finish 3 things, then the first 4 things, and then you add the first, and eventually if you add up lots and lots of things, if those adding up putting the next thing on doesn't make it change much, well then you think your series is going that place. So the kind of crazy thing that happens is you take this series and you make it into something called a sequence of partial sums. And the partial means you sum up part of the series. So like S1 is just the first term. S2 is the first 2 terms added together. Does that make sense? S3 is the first 3 things added together. And then those S's, they make a list, which is a sequence. So you take your series, turn it into a sequence. And if this sequence of partial sums converges to some number S, then that infinite sum goes to that number S. What you should think about in this Sn, n is the number of terms you have added. Does that idea make sense? So you took a series, made it into a sequence. It's unfortunate both these things begin with S. Okay, you've got to keep them straight. Sequence, list, series, sum. Yes? Yeah, but when you had sequences, the numbers in the sequences were different. Like the first number in the sequence wasn't the same as the second, was it? No, and so that's kind of the idea. Even though, yeah, they're definitely going to be different, for sure. But that's okay. Sequences, there's no requirement that says that the first number is the same as the second, it's the same as the third. Okay. So this first one. So for now, just to start with, the only way you know how to find the sum of a series is to find the S sub n thing, that is the partial sum of the first n things. So S sub n means you add up from wherever this series starts up to n. So if you're plugging 1 into this expression, what do you get? 1/2.
Oh, this is exactly the thing you just showed.
Yeah. When you plug in 2, what do you get? A quarter. 1 over 2 squared, or a quarter. When you plug in 3, what do you get? An eighth. And then I didn't give you a specific ending point, so the way you symbolize, okay, the pattern keeps going, you say dot, 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 plus what would be the last thing you'd plug in?
Take it to infinity, it goes to 0.
1 over 2 to the n. That's like the n is the last thing you plug in. Like if I'd said S10, that means you plug in 10's the last number you plug in. And yeah, all I was pointing out with this one is that this is the example that we just looked at about Zeno's paradox. So for now, let's just say that this is going to equal 1. There is a way to prove that we'll learn a little bit later in this lesson, but for now, just kind of reasoning through that, we're just going to say this is equal to 1. Okay. But the idea that you list, but then that wasn't like we looked at the partial sum and looked at what happened or anything, but there definitely is the case that 1 over 2n term as n gets big is definitely going to 0, right? Okay. So the next one is a special one. This one's called a telescoping sum. So let's like write this next to it so you have a name for it. It seems like you guys are all better at stuff when we give it names.
Mom gives you something to remember.
I understand. Okay. All right, so let's just write down what the partial sum is. List like the first 3 or 4 things. So first, input 1 into that expression.
Can we start with 0? No, we can't.
We cannot start with 0 because of division by 0 and because the series, the little bottom index there, said to begin at 1. So start with 1. So when you plug in 1, you get 1. Well, don't combine the terms, okay? I'm sorry, I didn't clear that. 1 plus, or 1 minus 1/2. Sorry, don't simplify. I should have specified that. Okay, there's a reason for that. Okay, when you plug in 2, what do you get? A half minus a third. So you plug in 3, what do you get? A third minus a quarter. Is everyone okay with that?
Oh, you're canceling everything out except.
Yeah, look at what happens. So, you see, these guys, they're going to cancel, right? These guys, they're going to cancel. Now, I want your expression for Sn to be correct. Like, I don't want you to get problems right because you're lucky. I want you to get them right because you know what you're doing. So, if we've found, like, an expression for Sn, n is the last thing we plug in. So, at the end of my sum, my like, little partial sum, I have 1 over n minus 1 over n plus 1. And one of those terms is going to cancel. It's just not completely clear which one.
So I think it's going to be the 1 over n.
It is, but let's verify that with like an actual argument, okay?
Okay.
So first of all, is everyone okay that this is the last thing you do is you plug it in and that gives you that? Okay, now when you go 1 previous, what happens to the denominators? Are they going to decrease or increase?
Decrease.
They decrease by 1. Does that make sense? Like from this 1/3 goes to 1/2, right? This 1/4 goes to a third, right? So the term prior to that, what's it going to be?
And minus 1.
1 over n minus 1, and then minus
1 over n minus 1 plus 1.
1 over n plus 1, but then you minus 1, which makes it
One
n,
half.
1 over n.
I figured you wanted to.
Oh, sorry, yeah, no, that was not clear. Okay. And so then you see that there's some kind of cancellation pattern that's happening, right? So there are only 2 things that remain when you do all the cancellations. What are they?
First one is 1 over n.
Sn's 1 and 1 over n plus 1. Okay. So what this formula does is it lets you sum up the first n things. You want to sum up the first 100 things, what do you plug in for n? You want to sum the first gazillion things, what do you plug in for n?
Whatever a gazillion is.
Oh, does that make sense? But that's the idea, is this sums the first n things. And what do you want to do with the number of things you're summing? You want to take the number of things you sum to infinity. And that will equal the actual sum of that infinite series. And it's a really easy limit. Where's it go? 1. Can you see why they call it a telescoping series?
Kind of.
'Cause it kind of like collapses in on itself like a telescope does when you put it together.
Yeah.
Telescoping series don't always have to have the pattern that things cancel in easy succession. It might be that something in this first term cancels something in the third. So the whole idea of like listing out stuff and then looking for the cancellation pattern is the only way to do it. And they're all a little bit different. But the basic idea is you find this expression for Sn, which is your partial sum, and where n is the number of things you sum, you take the number of things you sum to infinity, and that's what your sum is. So that big old honking thing sums up to 1. Okay? Is that all right? Okay. All right, this looks deceptively simple. And who else had the first impression that this should converge?
It doesn't.
It doesn't, yeah.
This is actually n over n, right?
Yeah, so what this really means, let me work it through and then check. Okay, what this really means is your first partial sum, S1, is just 1. Your second partial sum is 1 plus 1. Make it 1 to itself again. Okay?
So it goes to
Which is the same thing as 2, right?
yeah,
What's your nth partial sum going to be then?
infinity or n.
N, yep. And then the limit as n goes to infinity of Sn is equal to infinity, yep. And so this series does what? Diverges.
But you could have made a weird argument if you'd written one as n over n, which would have been equivalent.
I don't know why that'd be helpful, but okay.
Well, it'd do the same thing.
Yeah. How about this next one? N squared. So let's just write down what Sn is. Sn would be, first you plug in 1, you get 1 plus, plug in 2, you get 4 plus 9 plus, all the way up to n squared, right? Is that going to go to a number or is that going to go to infinity? That's definitely going to go to infinity. Limit as n goes to infinity of Sn is infinite, so the series diverges. Okay.
When you teach us that way to prove it, do you want us to write that down on a quiz?
Yeah, to prove it, I'd like you to, well, we'll have some different criteria to show you. Like, there'll be an easier way to tell that. Show you only, at the end of the lesson, the thing you'll only really need to show partial sums for is the telescoping stuff.
All right.
Because we'll learn some shortcuts that let you not use those things. Does that make sense?
Yeah.
Okay. Alrighty. Find the sum of this guy. And at this stage, the only thing you have to work with is partial sums, right? And you've got nothing else. So we're going to actually use something we did in chapter 7 to make this into a telescoping series. And the thing used from chapter 7 is you use the partial fraction decomposition. I know it's your favorite, but it's an easy one, yes? So how does n squared minus 1 factor? N plus 1, n minus 1, yep. Oh, there's another reason. Why did I start my series at 2 and not 1? Denominator would be 0. If that ever happens on a homework problem, I probably made a typo. Okay, because it definitely was never intentional that I'd do something like that. So a over n plus 1 plus b over n minus 1. And then you multiply both sides by the denominator of the left, correct? So when you do that, what do you end up with?
A times n minus 1.
2 equals a times n minus 1 plus b times the other one, yep. You do that because I don't know what else to do with this thing. I mean, you also do it because the denominator factors. That's a pretty good hint. Does that make sense? You could just plug in numbers, but I don't think it's going to work as well. The only things you know how to work with are these partial sums, and one of the common things with that is this telescoping pattern. And so part of the practice is just knowing to recognize that that's going to happen. And it often happens, well, you'll see more when we get the A's and B's that this is going to occur, okay? So what happens when you plug in n equals 1?
You get 2 equals 2.
You get 2 equals 2b, and therefore b is 1. And when you plug in n equals -1, you get 2 is negative 2a, and a is -1. Okay, so sort of saving that, we can make this series into a sum from n equals 2 to infinity. Can I write the b first and the a second? Is that going to make anybody sad?
Nope.
Like write 1 over n minus 1 minus 1 over n plus 1? Is that okay? I just flipped them because I just don't like having the negative in the middle. It makes me feel better.
I feel like there should be some cancellation.
And now this is where you can tell that the cancellation is going to happen. When you have something minus something that's quite similar to it, that's how you know you're going to have that telescoping partial sum thing happening. But this one had that added level of trickery of having to do the decomposition first. Does that make sense? So now with this stage, we list what the partial sum is. Okay? So when you're doing that partial sum listing, what's the first number you plug in? 2. So plugging 2 into the first part of this expression, we just get 1, right? How about the second one? Minus 1/3. Good. Okay. Then you plug in 2, and you end 3. Sorry, 3 is 3. Yes, you plug in 3, and you get a half minus. Okay, and don't freak out. Okay, like nothing cancels yet, but don't panic. So, okay, no panic. Plug in 2, 3, 4, and we get minus. And just make yourself feel better. Also plug in 5. You get. I think you get a quarter minus a sixth. Yeah. Okay. So I warned you about this, yeah. So this negative 1/3 will cancel with that 1/3, right? The
1/2 hasn't gone away.
The 1/2 hasn't gone away. Is it going to go away?
Probably not.
No, because everything, the denominators are getting bigger, right? Okay, so then, but will the 1/4 go away? Yep, and eventually will the 1/5 will go away in the next term, then the 1/6, right? But the 1 and the 1/2 are there to stay, right?
And probably something at the very end.
And actually, this is a pattern that always holds true. If you have 2 things at the beginning, you're going to have 2 things at the end as well. Like the previous one, we had 1 thing at the beginning left, there was 1 thing at the end as well. So let's just start and list backwards. So the nth term is 1 over n minus 1 minus 1 over n plus 1. Like that's what you get when you plug in n. So then go backwards 1. What does the 1 over n minus 1 become?
1 over n minus 2.
1 over n minus 2. And how about the 1 over n plus 1? 1 over n. Very good.
And that's like
And nothing obviously cancels yet, but let's just go back 1 more and see if we can see the pattern. Okay, that becomes 1 over n minus 3. Yep, right? And then what is the second term? 1 over n minus 1.
So that would cancel that.
So you can see this guy is going to cancel that guy. And if you go back 1 more, you're going to get canceling out the 1 over n minus 2, right? Okay, so then fill in like some ... so I know there's like, there's stuff in the middle there. So S sub n is going to equal that 1 plus a half is 3/2. And then we have minus 1 over n and minus 1 over n plus 1. Everything else in the middle is gone. And so how do you find the sum of the actual series? Take the limit, yep. The limit as n goes to infinity of Sn. And this really doesn't even work at all. What's that limit going to equal? 3/2. So your series converges to 3 over 2.
Isn't that the same idea of never quite reaching that thing?
Yeah, exactly. Same idea as that whole idea with, what's it called? The paradox. Yeah. Okay. So another So for telescoping series, your only option is to go to that whole partial sum definition. You have no other technique to work with yet. We're going to use that partial sum definition to find a sum for a specific series called the geometric series that happens a lot. Now, one thing about this is I chose to present this differently than your textbook because I think your textbook's way is a little bit more confusing. So just keep that in mind, and you can look at theirs and we'll talk about why it's the same, I think, next time. Okay, but the one thing here is that this series starts at 0. Okay, that's one thing that's different. So a geometric series has the property that it is a number a times some number r to the n. And we know that this is going to converge if the absolute value of that r is between 0 and 1, and it will diverge if that r is bigger than 1. And if it converges, you can use this formula to figure out what it converges to. Okay? But of course, you're like, well, how the heck do you prove that formula, right? Like, it doesn't make no sense. So what we're going to talk about now is how to prove that that's what things add up to, okay? And we start with the whole partial sum definition and a little bit of a clever trick. So the partial sum. So the trickier thing here is you actually have to begin at 0. So when you take this expression, a r to the n, and you plug in 0, what's r to the 0? 1. So that's where you just get a from. Does that make sense? So you have a. Plug in 1, you get ar, right? It's like Pirate Day math. Plug in 2, you get ar squared. Sorry. Okay, I'll stop telling bad jokes. Just fail as a comedian. And then you plug in n and you get ar to the n, right? Okay. Now I'm going to do a clever thing. Here's my clever thing. I'm going to take that s sub n and I'm going to multiply it by r. Okay? What happens when you do so you get AR, right? Plus AR squared. I don't know why I forgot my R, sorry. AR squared.
Shouldn't there be an A over R there?
No. What I did is I took Sn, which is equal to this, and I'm multiplying both sides by R.
Oh.
You see what I'm saying?
Okay.
So on like the right side is like massive distribution of R. Okay, what do I get next then after AR squared? AR cubed. What's the last term going to be? N plus 1. Right, because R to the n times R, those exponents add, right? What's the term 1 prior to that? AR to the n. Right, because every time I get the next term, the exponents are increasing by 1, right? Okay. So here's how you employ that clever trick. To prove this formula, what you do is you take Sn minus R times Sn. And that kind of has some elements of being a little bit telescopy in it. Do you see what I mean by that? Say that again? Where'd the Sn come from? Sn is right here. But they're two different things. I have Sn and I have R times Sn. Sn is equal to this. R times Sn gives me that. They're related and they're very similar, sure, but that's... Okay. And if you take that and you do the top thing minus the bottom thing, what happens to crap tons of stuff? They cancel, right? You end up with like that whole top thing, and when you do AR minus AR, it's gone, right? Does that make sense? When you do AR squared minus AR squared, it's gone. What are the only things that are left?
A and AR plus 1.
So you'd have A, and then it'd be minus AR to the n plus 1.
Oh yeah, because subtraction.
Because of subtraction, right? So I took that whole, I did Sn minus RSn, which is the same as taking this big long thing minus parenthesis this big long thing, right? Okay, and now we're going to take that and we're going to solve it for S sub n. So on the left side, S sub n is the greatest common factor, right? So that's S sub n times 1 minus R. And then on the right, is there a greatest common factor? A, yep, A times 1 minus r to the n plus 1. And then solving for S sub n is A 1 minus r to the n plus 1 over 1 minus r.
I'm not seeing how that completely gets down to,
Yep, I get it. So that's just the first step. So you're okay with how we found that S sub n in the first place. Okay, now here's the little bit of the magic bit. It's not really magic, but. So if your absolute value of r is bigger than 1, actually even equal to 1, I'll start with bigger than 1 because I don't know why. There's definitely a typo in there where I said, no, equal to also happens. No, yeah, definitely diverge, but I'm having a problem with equal to now because my notes don't say what to do with that. Let's leave off equals for now and I'll come back to that tomorrow because I'm just going to waste your time. So if r is bigger than 1, what's happening to raising that number to a power? So think exponential growth, right?
it's going to be much bigger.
Does that make sense? That's what this is, exponential growth then. So this is going to go to infinity, right? 1 minus infinity, well, that's just going to make some negative number of some sorts, right? Anyhow, if this goes to infinity, what's going to happen to your Sn? You don't know if it's infinity, but you do know it does what? You do know it diverges. And the reason, maybe this goes to negative infinity. Does that make sense? You can diverge both ways. If your absolute value of r is less than 1, what does this r to the n plus 1 look like? You've got a number that's less than 1 and you're raising it to bigger and bigger powers. Doesn't that look like exponential decay? Which, as n goes to infinity, that thing's going to go to 0. Okay, and I managed to, in thinking those two things through, figure out my freak-out process. When n is equal to 1, what you get here is the sum from n equals 0 to infinity a times r. And that diverges for the same reason that 1 diverged. Does that make sense? So 1 also diverges.
So you get AR, 2AR.
You get 1AR, 2AR, 3AR, it's going to diverge. So that's why that formula is what it is. And so this whole thing happening tells you that this piece is going to go to 0. And so that partial sum is going to go to a over 1 minus r. But the kicker with this formula, and I'm going to fix that one typo that I made in here. So this thing right there, that should not say equal to. That should just say less than.
It does in other.
It does in your notes? Okay, yeah, good. I've definitely fixed it then. Okay, spectacular. All right, so when using this formula, there are two important things. Thing one, find r, okay? To figure out what is your radius, and then check if the absolute value of r is less than 1, okay? If it is, it converges. If it's not, it diverges. Once you've checked that, make sure your thing begins at 0, because this formula depended on it beginning at 0, but beginning at 0 made our partial sums what they are, and if the doesn't start at 0, you've got to do this thing called reindexing to make it start at 0, okay? Okay, so let's try a couple. So 5 over 3 to the n. So first thing, let's find the r. And it wouldn't be bad to check the first thing, does the series start at 0? Does it start at 0?
Yes.
Yes, so no worries. And it's 0 to infinity. Can I rewrite this as 5 times 1/3 to the n? Does that make sense? So seeing something raised to the nth power is a hint that it's a geometric series.
And also is a hint that that's probably the r.
And also the thing raised to the n is also the r, exactly. So in this case, in the geometric thing, what is the a? 5. And what is the r? 1/3. And as the absolute value of r is less than 1, this series converges. And it probably would be really, really good, and I think I probably should require this, that at some point in time you should say that this is a geometric series. As in, this happens often enough, it's good to know what its name is. So probably put that first. This is a geometric series, and as r is less than 1, this series converges. Okay? And it converges to a over 1 minus r, which is what?
15 halves.
5 over 1 minus a third, right? Which is 5 over 2/3, yes, which is 15 halves. And with geometric series, there is no need to do partial sums, okay? The proving of that formula did the partial sums to prove it, and you don't have to use them ever again for a geometric series, okay? Telescoping, you have to. There's no other way. I'm not withholding it from myself. Okay, here's one. Did I fix your notes and put an infinity up there? Okay. Oh, man, it begins at 1. Crap.
How do you reindex?
How do you reindex? We really want this to be, so in my past class, I just told people to think about it, which maybe isn't the best method. So let's try this other way. So you want that to be 0, right?
Yeah.
So make a new letter. Let's call it K. And K, how much do we want to take away from n to make it 0? 1. K is n minus 1. It's kind of like a substitution of some sorts. So if n is equal to 1, what's k going to equal?
0.
0. So, and how about if n is equal to infinity, what's k going to equal?
Infinity minus 1.
Infinity minus 1, but that's still infinity, right? So this can become sum from k equals 0 to infinity. Now the question is, what do we do about that little n there? What could you replace it by? Well, k is equal to n minus 1. So, yeah, so therefore n is equal to k plus 1.
So this is exactly like changing the bounds on an integral.
It's a lot like changing the bounds on an integral. And actually also another way you can convince yourself that they're the same thing is just plug in some numbers. Like in the first one, when you plug in 1, you get 5 over pi, right? When you plug in 2, you get 5 over pi squared. Does that make sense? In the next one, first you plug in 0, you get 5 over pi, right? And you plug in 1 and you get 5 over pi squared. See what I'm saying? Like they are the same thing. It's just that this one, you first plug in 1 to there you first plug in 0. But they give the same things. Okay. So now it's almost ready to go into the geometric formula. What else could you do? You got pi to the k plus 1, not pi to the k, right? So what you do here is you pull it off and make it into k equals 0 to infinity, 5 over pi times 1 over pi to the k. Does that make sense?
And that works? No, that works.
It does work, doesn't it? Because I just sort of like, when I multiply exponents add, I just kind of undid that, right? Okay. So now this is a geometric series. Trick. What's the a? And what's the r? 1 over pi. And do you know 1 over pi is less than 1? I mean, well enough, right? So this converges.
That would
To
be exactly what that would be.
a, who cares? A over 1 minus r. So 5 over pi over 1 minus 1 over pi. And you could get a common denominator and reciprocate, or you could just multiply the numerator and denominator by pi. Does that make sense? If you did that, what would you get? 5 over pi minus 1. And so now you do know what that is exactly. It's that. Just happens to have a pi in it. I mean, you know. But now, here, one related thing. What if this had been n equals 2? How would you deal with that then?
K equals n minus 2.
You do k equals n minus 2. It's like you look at that starting index and you say, how do I make that 0? Does that,
How would that change your
if that had been
moving k?
n equals 2, you would have let k equal n minus 2, and then your n would have equaled k plus 2. And then that would have changed this to a pi squared. Does that make sense? So, okay. That reindexing thing definitely is the trickiest bit, for sure, I think, right? Okay. Here we go with this one. Like, whew, starts at 0. So this one, you got to pull it apart a little bit and find the a and find the r. Oh, exponent rules. Algebra 1, how we love you. So I think this is 3 times negative 3 over 2 to the n power, right? By that? Let me do it in 2 steps if you took some people a minute. So first of all, are you cool with me pulling off the 3? Yes? Then I have 3 to the n over negative 2 to the n, right? So can I write that as one big fraction to the n then?
Yes.
That's what I mean. So you have a sum from n equals 0 to infinity, 3, and then negative 3 over 2 to the end. Doesn't matter where the negative goes. It can go on the top or the bottom, whatever. Okay? So this is a geometric series. What is the a? 3. What is the r? Negative 3 over 2. Okay, and when you're checking for convergence or divergence, you look at the absolute value of your r. Yeah?
Wouldn't we need to have 9 in the original formula?
I just couldn't hear that. Say it again.
Would you need to have 9 in the original formula
Would you need to have 9 in the original formula?
to the n? Because you did 3 times 3 to the n. So would you need to have 9?
No, you're messing up exponent rules.
Oh.
What's 3 squared times 3 to the 5th? 3 to the 7th, right? That's what we were using. So yeah, definitely it's not 9. Yep. That's 3 to the 1st, 3 to the n. That's where 3 to the n plus 1 comes from. Does that make sense? Okay, great. So the kicker with this geometric formula is look at the absolute value of your r, and if that absolute value exceeds 1, then you diverge. So this absolute value is to 3/2. Is that bigger than 1 or less than 1? Greater than 1. Therefore, the series diverges.
Well, I just wrote absolute value 3/2 is greater than 1, or negative 3/2, I guess.
But that's how you check. Does that make sense? Okay. The next one's evil for many reasons, right? A couple of which, so, okay. So let's worry about the n equals 1 to infinity thing in a second. Let's deal with the whole fact that I have powers to powers and stuffs and things, okay? So first of all, do you agree with this part? That 2 to the 2n, that's the same thing as 4 to the n.
Okay, that was.
Does that make sense? And the reason, that comes from exponent rules for multiplying, that 2 squared to the n, what happens to those powers? They multiply and give you 2 to the 2n, right? It's using that rule just in the other direction, right? You see what I'm saying? Powers to powers multiply. I can break this 3 into 3 to the 1st times 3 to the negative n.
Not, oh, there's no.
Does that make sense?
It
Because
does,
I unadded, right? Okay, so then I can write that as, make your n's into a ratio now. So I have 3. And then what happens to the negative n power? Goes below. So that becomes 4/3 to the n. Does that make sense? because the 3 to the n goes down, and we got 4/3 to the n. And I claim at this stage, you don't even have to re-index. Because why? It's already gonna, your R is equal to 4/3. It doesn't matter if you re-index. If you re-index, A changes, right?
Yeah.
But R doesn't change. So as R is equal to 4/3, and the absolute value of R is bigger than 1, this series does what? Mm-hmm.
I was kind of expecting one of them to converge.
Well, we had those in the previous slides. And then we have example 7 will converge. Wait, this is, my notes are a little bit off. Yeah, this one diverge. I think example 7 will converge. I moved them around. But the point is one point on this one is that you have to remember your exponent rules from Algebra 1 in reverse. Like stuff like this, being 4 to the n, that's tricky, right? Yeah, okay. So technically speaking, you have before in your life seen examples of infinite series, and not just Zeno's paradox. One example of an infinite series is a repeating decimal. Okay, well, repeating decimals, you were told like back in Algebra 1 that they are rational numbers, right? And to be a rational number, it means that you can write that number as a ratio of two things, right? You can make it into a fraction. And so the question is once you've done like the division, how do you go backwards and make that thing back into a fraction?
Use the series.
You can use a series, and you can also use algebra. So I'll show you the algebra trick because it's easier, but I'll show you the series way as well. So the algebra way is to like let your number be something like x. And x is what you want to find, right? So you're just going to use a clever trick to solve for it. And the clever trick you employ is an awful lot like the clever trick used to prove the geometric series formula. So could you multiply, well, let me just do it and you'll understand why it's helpful. If I do 100 times x, what does that do to that decimal expression? Makes it 46.464646, right? Does that make sense? Why did I choose 100? And because if I put 2 decimal places, the patterns like line up again. Does that make sense? And then if you do 100x minus x, as in take the bottom number minus the top number, what happens to all the decimal stuff?
Good 46.
Bye-bye, right? And you just get 46. So then you have 99x equals 46, right? And therefore x is equal to 46/99.
Which I kind of suspected it was in the beginning.
Yeah, I mean, there's definitely a pattern that occurs there. You can actually use the same thing to prove that 0.999 repeating forever and ever is actually equal to 1. Okay, it's decimal expansions are not unique, which means that every whole number has 2 ways to write it. You can write 3 as 3 or 2 point lots of 9s. Okay, you can do the same trick and this is going to happen. Okay, I'm just telling you, like it will happen. So that's how you use algebra to show us, but here's how it's a. So these patterns occur in groups of 2, right? So think about that as 0.46 plus 0.0046 plus 0.000046, etc. Do you agree that those things added up make your repeating decimal? Does that make sense? Okay.
And that's just another way to write that.
Yeah, and then you use, this is just another way to write like this thing down, right? You add on 46 to the next 2 spots each time you go, right? And then you make those into fractions using properties of like placeholders. Like the first placeholder is a 10, the second placeholder is the hundredths, right? So 0.46 is 46 out of 100, right? As a fraction. So we have tens, hundreds, thousands, 10,000s, right? So plus 46 out of 10,000, right? And this next one's gonna 10, 100,000, 10,000, 100,000. Is that a million then? Okay, and you kind of get the idea. Another way to think about that is that's 46 over 100. 10,000 is 100 squared, isn't it?
Yes.
What do you think 100,000 is?
A million.
A million, sorry. Yeah, a million is 100 cubed. Does that make sense? Think about how we count the zeros thing, right? 100 times 100 times 100 is 1 with how many zeros? 6. And is that what you have? Yes. Okay. So putting that in a sum, and I'm going to start my sum at 1 because I think it's easier. And then you could reindex it. 1 to infinity. Does the 46 change? No. So you have 46 times 1 over 100 to the power of n.
And that's you.
And then that's your geometric series. I'm going to, because I have not all the time I wanted, you'd have to reindex and then, go from there, but you're going to get the same answer as algebra. On your WebAssign, I don't really care how you do it. Like the algebra trick is totally legit. Go ahead and use it, but this is how you make it into a series. Does that make sense? And if the pattern, I chose to make things over 100 because the pattern was happening in 2s. The pattern was just happening in 1s. Put stuff over 10. Does that make sense? Okay. If the pattern happened in 3s, it'd be over 1,000. Okay.
If you do 3 or 4, it'd be ridiculous with 1,000.
Ready for this guy? Is that what you have next? Okay. So this is called the nth term test. I'm afraid that I am going to often call this the, not yet, sorry, lied. Okay, I take that back. Restart. So if your sum converges, then the terms have to go to infinity. Terms have to go, why do I say things that I don't mean? If your series converges, then the limit of the terms has to go to 0. Does that idea make sense? If the things you're adding up have to go to a finite number, the things you're adding up have to get small, don't they? As in go to 0. Okay, so we're going to actually prove that. Okay, so when you prove things, you know the if part. So we're going to suppose the sum from n equals 1 to infinity of a sub n converges. Okay. And if something converges, we know that s sub n converges to some s, where that s sub n is the nth partial sum. So what it means for a series to converge is that its partial sums converge. And s sub n is going to equal what? It's the nth partial sum, right? Which means add up the first n terms. So like a1 plus a2 plus a3 up to a sub n. And what we want to show is that this thing happening means that the a sub n has to go to 0. Okay. So this is s sub n. What is the sum of all the things not including a sub n? S sub n is the sum of the first n things, right? How would I sum just the first n, one less than n things?
Minus a sub n?
Yeah, so that'd be s sub n minus 1. Does that make sense? So instead of going up to n, you go 1 previous to it. So that'd be a1 plus a2, blah, 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 plus a sub n minus 1. Do you agree with those two things? What that's going to do is let us write a sub n in a clever way, okay? Then do you agree that a sub n is equal to s sub n minus s sub n minus 1? Do you agree with that? If I take this thing, which is some of the first n things, and I take away this thing, that's some of the first n minus 1 things, and I subtract them, I just get the last thing. Okay. And once you have this, you're almost done. So this is true. And then the limit as n goes to infinity of an is equal to the limit as n goes to infinity of Sn minus the limit as n goes to infinity of S sub n minus 1. And where does this thing go?
To S.
To S. Does that make sense? That's what it means to converge. You go to some number S. We don't know what S is, but it goes to S. And what if you limited not like Sn, but Sn minus 1? Where's that going to go to? I mean, Sn minus 1 just means you add the first n minus 1 things, right? So you're kind of like one step behind. But if you go to infinity, it's still going to go to
So it'd be
S. Same thing. And so therefore that limit must be 0. This is, I don't know how much experience you have with if-then statements, but this one says if some an converges, then limit n goes to infinity, an is equal to 0. That's what it says, right? What it does not say, and everyone's going to try to say this at some point in time, it does not say if the limit as n goes to infinity, a sub n is equal to 0, then your series converges. That thing, first of all, do you know what that thing is called when you switch the if and then? It's okay if you don't.
Yeah, it's the inverse, right?
Almost. It's called the converse. So this is the converse. And this converse is false. Sometimes converses are true, but this one is false.
So it's an if and only n.
It's an if-then in the one direction, but not the other. If it goes both ways, it's called an if and only if. That's the technical thing.
I thought it was an if and only if one way, but then it wouldn't work the other way because you said that.
Nope. If and only if mathematically means both, works both ways. Here's my great, I think this is a good example of how things can work one way, not the other. So if it's raining, this implies the sidewalk is wet, barring some like weird place where the rain evaporates before it hits the ground. We're not California, okay? We're Alaska. If it rains, the sidewalk is wet, right? Okay, is the converse true? If the sidewalk is wet, does that imply that it's raining? No, because it could be sprinklers, right? Or it could be that it just rained, or it could be that somebody pilled in the sidewalk. So, but the point is, like, you see how switching that thing does actually change the implication sometimes?
Yes.
And that is definitely true with this. So if the limit goes to 0, the series may converge, it may not. Okay? You just don't know. So, and the next example is a proof of one of those. The proof is tricky, and I'm going to just skip it for a second and do it last. So we're going to, for this. Okay. Because this is the useful thing you're going to use. So this nth term test for divergence, some people call it the nth term test, some people call it the test for divergence, I don't care which one. It says that if your terms don't go to 0, then your series has to diverge. And that comes from the theorem we had above.
And then it would be, if it doesn't, if it diverges, then it doesn't go to 0?
Yes. So what the thing is, if the a sub n's go to 0, like the things inside your series, if they go to 0,
They have a chance of,
yeah, you might converge. That's called a necessary but not sufficient condition. Which means it's needed, but it's not enough. Does that make sense? You have to have it, but it's not in and of itself enough. But that means that if you need it and it doesn't happen, then convergence can't happen either. Does that make sense? You need these things to go to 0 just to have a chance. And if they don't go to 0, you ain't got no chance. Okay? Does that make sense?
so that one would be an if and only if. The one above that.
Kind of. So this one, So when you look at a series, one of the first things you always should check is look at the terms inside and see what happens to them as n goes to infinity. If they go to 0, you might converge, you might diverge, you don't know. But if they go to not 0, you diverge for sure, okay? So you find the limit as n goes to infinity of n squared plus 1 over 2n squared minus 5. And in the interest of having, like, time to talk about the last one, what is this limit just going to equal? Just tell me. It's 1/2,
So is that
which is
a problem?
not equal to 0. That means as you plug in bigger and bigger numbers, this stuff you're adding together gets closer and closer to 1/2, plus 1/2, plus 1/2, plus 1/2. Does that make sense? Kind of like the whole thing with the 1 diverged, right? So thus, this series does what? Diverges. And we'll say by the test for divergence.
But it's opposite than,
That sounds almost like freaking.
Say that one more time.
it's opposite than normal because why?
It's opposite the what?
Because like before, if it goes to
Oh.
some number, it converges.
Oh, okay, good question. So, the sequence where a sub n is equal to n squared plus 1 over 2n squared minus 5 converges to 1/2, okay? Like the list converges to 1/2. But the series where you add up the a sub n's, that's a great thing to point out, diverges. You guys see what the point was there? That if you just had a list, it goes a place, right? But when you try to add up the stuff in the list, that goes to infinity. So that's the difference. The list converges, but the sum does not. Does that make sense? So you use the limiting stuff we learned in the last lesson to do this. Yes?
So a series is really similar to an integral to a function.
Yes, it is very similar to those integrals we had that went from like a number to infinity. And we're actually going to use those integrals to prove certain series converge or diverge. Yay.
It just feels really similar.
It is, you're right, it is really similar, definitely. Okay, let's do part B and we'll come back and do example 8 next time, okay? Yeah.
You got that 1/2 is use the L'Hopital's rule, just making
You could use L'Hopital's or you could divide by like 1 over n squared. Yep, either way.
sure.
Nope, you were not missing anything. Okay, this one, the limit as n goes to infinity of ln 5n plus 1 over n plus 1. We did a few like this when we just had sequences last time, right? What can happen to the limit? Where can it go?
5, ln 5.
It goes inside the ln.
Well, that could happen too.
Yep. And then the stuff inside the ln goes to 5. And you know, is ln of 5 equal to 0?
Probably not.
Probably not. Well, ln of 1 is 0, but 5 is not. So thus, the series diverges.
It seems like that's going to happen a lot.